So far, we have covered framing and an overview of error control as part of the data link layer. In this video, we are going to cover error detection in detail. Before we proceed, a quick quiz. As part of the error control, we saw the framework that of adding k redundant bits to the message, and we also covered the general idea behind error detection and correcting codes, that of Hamming distance, and what the design goals of some of these algorithms are. So basically you add k redundant bits to an m-bit message where k is derived through some algorithm. At the receiver, you employ the same algorithm to detect errors and take corrective action if necessary. So this is the framework on which we are going to build. A very simple error detection mechanism is the parity bit, which you must have encountered before. So here is even parity. Basically, you set the parity bit such that there are even number of ones in the code word. So here there are 2 ones, so you set the parity bit is equal to 0. So what do you think is the error detection capability of this? You think it can correct any errors? So parity bit can detect any odd number of errors because with this the parity will not match anymore. And unfortunately it cannot correct any errors because you just have one bit and it does not give you any indication of where the error has occurred. Wherever error has occurred just shows that the parity does not match. A more sophisticated version of parity is the two-dimensional parity, where you take parity of the row as well as the column. So this is also even parity. As you can see, there are 4 ones. That is why you put the parity bit equal to 0. And similarly, if you look at here, there are odd number of ones, thereby you put the parity equal to 1. So this error detection mechanism is used by the BiSync protocol for ASCII characters, which are basically represented by 7 bits. So if you are working with blocks of n ASCII characters, how many redundant bits do you think you add as part of two-dimensional parity? So that's right, you use n plus 8 bits of redundancy. This n arises from the fact that for each of the n characters, you are adding a parity bit, and you are adding one parity byte for the columns that corresponds to 8 bits. That it can detect 1-bit errors is obvious given that the previous one-dimensional parity itself was able to do it. What do you think? Do you think it can correct 1-bit errors? Yes, it can correct 1-bit errors. For example, if the 0 were to get converted to 1, you will notice that this parity bit and this parity bit are going to be in error. So based on this locations, you can conclude that this bit is in error and thereby correct it. So do you think it can detect 2-bit errors? That's right, it can detect 2-bit errors. For example, if this bit and this bit were in error, you will see that this parity will capture it as well as this parity will capture it. Note that this may not be able to capture it, but you still know that it is in error. What about correcting 2-bit errors? Do you think this two-dimensional parity can correct 2-bit errors? Unfortunately, you cannot correct 2-bit errors. Suppose, let's say these 2 bits are in errors. Okay. Now this parity is fine because both are flipped, whereas you will see that these 2 parity are going to be wrong. But you really cannot tell which of the rows the errors have happened. So in general, the two-dimensional parity can detect all 1, 2, 3-bit errors and it can detect most 4-bit errors. So its capabilities are not so bad. So another error detection algorithm that is used is internet checksum. This is not used at the link layer. In fact, it's used at the network layer, and the checksum is carried over the IP header. But since it's part of error detection, I'm going to cover it here. Now, as part of this algorithm, whatever data over which you want to perform checksum is viewed as a sequence of 16-bit integers. And now all you do is add up these integers using 16 bits ones complement arithmetic. So in ones complement arithmetic, you do regular arithmetic over the bits, but the carry typically gets added back to the sum. So here is an example. Suppose these are 4-bit integers and I'm doing ones complement arithmetic. I'm just going to add them up. 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 0 with a carryover of 1, right? Now this carryover has to be added back. So I'm going to add it back here. So the resulting thing is 0, 1, 1, 1. So this is a 4-bit ones complement arithmetic performed over these two integers. So what you do here is similar, except that you are doing arithmetic over 16 bits, and finally once you obtain the addition, the sum, you're going to take the complement of the result. This is the checksum. I'm going to cover an example, so that should make this clear. So at the receiver, you perform a similar calculation on the received data and compare the result with the checksum. If they don't match, definitely there is error, but if they match, very likely there was no error. Why likely? Because you can never be sure unless you know the error pattern. So here is the promised example. So IPv4 header, I'm representing in hexadecimal. Hexadecimal, each 4 bits is represented in this fashion. So this word is a 16-bit word, and there are many such words over which I want to calculate the checksum. So the first thing I'm going to do is add them up. I can potentially use 32 bits to add them up, and this is the addition result. So I have some carryover. Now this carry is added back to this sum, the 16-bit sum. So since this is a 2, the C has become E. So this is the ones complement addition over the 16 bits. Now I'm going to take the complement of this. If I take the complement of this, this is going to what is going to result in, and this is the checksum. Why am I taking a complement? That will become clear shortly. I presume people know what a complement is. So for example, if you have this, the complement of this is this. Basically flip the bits. So at the receiver, you take all the words, the 16-bit words that are part of the header, but this time you include the checksum also, and then you just add them up, basically using 32 bits. So if you did that, this is what you're going to get. So you have again a carry. Since it is ones complement, you have to add the carry back. So when you add the carry to the sum, this is what you're going to receive. So this corresponds to a 0 in ones complement. So 0 can be represented by FFFF or 0000 in ones complement. So why did we take a complement here? So taking a complement is basically negating the integer. Now when you take the complement and add this checksum back here, basically you are ensuring that the sum adds up to 0 in ones complement addition. Now comparison with 0 is a lot easier than comparison of two numbers. So that is why you take a complement here, so that once you do this addition, you can quickly compare it with a 0, whether it equals a 0 or not equal to a 0. So this is mostly an implementation artifact. So what do you think is the error detection capability of this code? Do you think it will be able to detect 1-bit errors? So this is straightforward. If there's a 1-bit error, the sum is definitely not going to match. Do you think it can detect 2-bit errors? So here is a hint. Think in terms of arithmetic. So that's right. This internet checksum is not very strong in detecting errors. For example, if you have a pair of single-bit errors, one of which increments a word and other decrements a word by the same amount, the sum is going to stay the same, and thereby it fails. Then given that it is so, it can't even detect 2-bit errors, why is it used still? For one, it is very easy to implement in software and it can detect some errors, but more importantly, majority of the errors are picked up at the link layer, the data link layer, where CRC is implemented, and CRC is a very sophisticated error detection mechanism. So all you need to capture are some residual errors, which this does fine. So we've been hearing about CRC for quite some time now. So here it is at last. So it stands for cyclic redundancy check. And this is used by many link level protocols, HDLC, DDCMP, Ethernet, token ring, so on and so forth. And there is some powerful math based on finite fields behind it. So before we get to this, we need to cover some background. So I'm going to give a brief overview of polynomial arithmetic. So in polynomial arithmetic, you represent an m-bit message with a polynomial of degree m-1. So here we have an 8-bit message which I am representing by this polynomial. So this corresponds to x to the power of 0. This is x, x square, x cube, so on 4, 5, x6, x7. So as you can see, since these coefficients are 1, only x7, x6, x2 and 1 are represented. So when you're adding or subtracting these polynomials, those additions are carried over a field of integers modulo 2. That means basically the coefficients are always going to be 1 or 0. So here is an example where I'm adding x and y represented by these bits. So here 1 plus 1 is 2, but I'm taking modulo 2, that becomes 0. So remember, there is no carry here. You just start doing modulo 2. So 1 modulo 2 is 1, 1 modulo 2 is 1, 1 modulo 2 is 1. So x plus y here is equal to z. So when you're doing arithmetic over the field of integers modulo 2, it turns out that addition and subtraction are identical. Basically, it boils down to XOR. As you can see here, this is nothing but Z is an XOR of X and Y. Just to show that addition and subtraction are identical, let me do the following addition. So here I have added x plus z and what I got is y. So I'm representing it here. But if you see here, this y is nothing but z minus x. And note that x is not equal to 0. So y is z minus x and y is z plus x with x not equal to 0. That means that addition and subtraction are identical as far as the field of integers modulo 2 is concerned. So the polynomial division is very similar to integer division. So for example, if you are dividing x over y, x can be represented in this fashion where q is the quotient and r is the remainder. So for integers, this r is always going to be less than y. So for polynomials, it is similar except that the degree of the remainder polynomial will be less than the divisor polynomial. So we will cover an example later, so these things should be clear. But with this background, let's see what CRC does.